Okay, good morning, class. So this is the second tutorial session. In this tutorial session, I'm going to discuss with you some of the questions in the example sheet 2. I suppose you have already tried to do some of the questions in example sheet 2, and maybe you will find some question difficult. Would like me to walk you through the solution. So let me ask, because I may not have enough time to go through all of them, just let me ask, let me know which question you find difficult and would like me to show you the detailed work, how to get the solution. Anyone? Any question you find it difficult in example sheet 2? That particularly you would like me to walk you through the solution. If you have no suggestion, then I will start from the last one and then going back from 7 to 6 to 5, because usually those questions put at the last of the list of the example sheet will be regarded as difficult. So in question number 7, have you tried to do question number 7? So in question number 7, we have a sample. Now actually the sample has a size of 6 because there are 6 numbers given. 9, 13, 6, 8, 10, and 13. So there is a typo here. There should be S1 up to S6. Now we have a sample of size 6. These are observed data. And we believe that this sample was drawn from a population that is Poisson distribution. I guess all of you have already learned about Poisson, right? Just let me know when I'm explaining. If you find something that you've never learned before, or you have some question, you have some problem in understanding what I just said, just let me know. Okay? So we have Poisson distribution with parameter lambda, but the lambda is unknown. It is an unknown parameter. This is population quantity that we don't know. But we believe that it takes only 2 values. Either it is equal to 10 or equal to 12. I don't know why we have this belief, but just assume that we have this belief. There are only 2 values for lambda. And the question is asking us to do a probability calculation to calculate the joint probability for the observed sample based on the 2 parameter value. Lambda equal to 10, we compute a joint probability. For lambda equal to 12, we compute another joint probability. Okay, so this is what the question is asking. So first, how can we find the joint probability? I guess you should have already learned about what it means by the joint probability. A joint probability is the probability of observing the whole sample. That is, the first observed data is equal to S1, the second observed data is equal to S2, and so on. And we have a sample of size 6, so there are only 6 pieces of data that were observed in the sample. So this is the joint probability. But this joint probability is computed from a Poisson distribution with unknown parameter lambda. So usually, to indicate its dependency on the value of lambda, it depends on the value of lambda. So we have this notation. We put a lambda on the right hand side of a vertical bar, to indicate that this probability will depend on the value of lambda. And we are going to compute this based on the two values of lambda. So in general, this joint probability, if we have a random sample, if these X are drawn from a random sample, then this joint probability can be computed by multiplying the individual probabilities together. So it is equal to the product equal to this, right? Okay, at this step. So in any step, if you have problem to understand, just let me know. Okay. So this is notation of product. We are multiplying all these probability together to get the joint probability. Now, what is this probability? This is a probability of a particular observation from the Poisson distribution. So we use the Poisson formula. The formula for the Poisson probability, if you still remember, this will be equal to e to power minus lambda, lambda to power of the observed value, divided by the factorial of the observed value. This is the formula of a Poisson probability. Okay? So whenever you have a Poisson distribution, for a particular probability for a particular value, it will be given by this formula. Okay? And we have a product of these numbers. We have 6 of this probability multiplied together. So we can simplify it. First of all, e to the power minus lambda multiplied to itself for 6 times. That will become e to the power minus 6 lambda. And lambda to the power of each value. We are multiplying all these 6 together. Lambda to x1, lambda to the power x2, lambda to the power x3, up to lambda to the power x6. We multiply them all together, will become lambda raised to the power the sum of all these x. And we divide by the product of the factorials of each of the observed value. So this is just a simplification of this product. Now we already have the sample. The sample is given. This is the sample given. Okay. We have x1, x2, x3, x4, x5, x6 equal to 9, 13, 6, 8, 10, 13. So that we can actually first compute this sum and also this product. Based on the observed sample, we can compute the sum of the observed value of each data. We get 59. That's the sum. And the product is pretty large. Nine factorial multiplied to 13 factorial, 6 factorial, 8 factorial, 10 factorial, 13 factorial. So it is a very huge number. You use your scientific calculator, you may find that it is equal to 1.4823 multiplied to 10 raised to power 39. Very, very large number. So what we need to do is substitute into this expression. And what we are asked to compute is this probability when lambda is equal to 10, this probability when lambda is equal to 12. So we just put lambda equal to 10, and all these things into this expression, we get one probability. We put lambda equal to 12, and all these things into this probability, we get another probability. That will be the answer to this question. So for we put lambda equal to 10 into that expression, so that will become the first term will be e to the power minus 6 times 10. And then lambda raised to the power of the sum of the x, which is 10 raised to the power 59. And we divide by the product of all these factorials. And use your scientific calculator again. It will be equal to 5.907 multiplied to 10 raised to the power minus 7. So this is the answer, the first answer to this question, to this probability. Everything here? So this is the first small probability. Usually this is the case. This joint probability will be very small, especially when you have a large sample, because when you have a large sample, you are multiplying a lot of probabilities together. When you are multiplying a lot of numbers from 0 to 1, the resulted probability will get smaller and smaller. And we complete the second part. So this will be just routine calculation. Now this time we put lambda equal to 12 and do the same calculation again. And this number will become smaller. Okay. So this is the answer to the first part of this question. Is there any question? Now the second part is to ask us to compare these two probabilities. And we see that this probability is greater than this probability. Okay. So that means the probability for when lambda is equal to 10 will become larger than the probability when lambda is equal to 12. Later on, you learn about what we call the maximum likelihood estimation, and this is something related. Because we are given two numbers, we are not talking about a very general estimation problem, but we have a sample, and we have some unknown parameter lambda. And you are told that this lambda can only take 10 or 12. And if you're asked to guess what will be the value of lambda, the true value of lambda, and you are only given two choices, 10 or 12, which one should we choose? Which one will be an educated guess? 10, yeah, 10. Because the probability, when lambda is equal to 10, the probability of getting this sample is larger. So it is more likely. We call it the likelihood. You will learn the details later. Now, this kind of calculation seems to be clumsy. In practical situations, sometimes we may not really need to do all these clumsy calculations except in the examination. Right? We can use R. Now in R, there are a lot of useful functions to calculate this complicated probability for different distribution. For a Poisson distribution, if you want to compute a probability for Poisson, we use this function, dBPOIS. POIS stands for Poisson, D stands for distribution. For example, if we want to compute this probability, this means when we have a Poisson distribution where lambda is equal to 10, how likely that an observation of 9 will be obtained? The probability of getting a 9 from a Poisson distribution with parameter lambda equal to 10. And it will be equal to 0.12511. So you can use this function to calculate this Poisson probability without using the hand calculation. And of course, in this question, we are not computing just one probability. We are multiplying a lot of probability together for the 6 numbers in the sample. So we can use this command, if you still remember, we can input a vector so that the result calculated probability will become a vector. Now don't worry, all these will be put in the solution that will be uploaded to Blackboard. So this function, we input a vector into S, then this function will calculate a vector of probability for x equal to 9, for x equal to 13, for x equal to 6, and so on. So you can see the output is a list of numbers. So this is the probability when x is for x equal to 9. This is the probability for x equal to 13. Probability for x equal to 6. Probability for x equal to 8, and so on. And of course, the question asks us to multiply them together to get the joint probability. So we use the product function. This function, PROD, is the function that multiplies the numbers in a vector. So we multiply the numbers in this whole vector of probability. We get the answer that we calculated before. And of course, if you want to, maybe I use smaller font because the screen is not large enough. Okay. So if we want to calculate the probability for another lambda, like lambda equal to 12, we just change it into 12. We get the answer we compute. And you can just play around, like you try other numbers, 11, 9, then you see some other probability. And then you compare all these probabilities to see which probability is the largest. Then the value of lambda will be the so-called most reasonable guess. In fact, if you input 9.8333, then this number will become the largest. Now, how can we get this number? Then you will learn details later. Is there any question? For question number 7? Okay. Just let me know anytime if you have any question. Then we move one step backward to question number 6. Now, question number 6 is about the so-called sampling distribution. We have a very simple description of the problem. We have S1 up to S10 being a random sample from a uniform distribution between 0 and 1. And we are asked to calculate the mean and variance of the sampling distribution of the sample mean. Now notice that sample mean is the average of our observed sample. And the sample mean itself is random. The sample mean itself will have its own distribution. And this distribution may not be the population distribution. In fact, the sample mean here does not follow the uniform distribution. And it has its own distribution, it will have its own behavior. And we would like to study its probabilistic behavior, like the expectation, the mean, and also the variance. And we have a formula. In general, what is the expectation of the sample mean for a random sample? Any idea? What is the expectation of the sample mean? This is something that was taught in the lecture. Expectation of the sample mean? It is also a mean, but it's not the sample mean. Expectation of the sample mean is also a mean. It is equal to the population mean. Now, this is a mathematical fact. Whenever we have a random sample, we, based on the sample, construct a sample mean. the expected value of the sample mean, the mean of the sample mean, is equal to the population mean. Now, sometimes students may easily get confused with this so-called mean of mean. What does it mean? That means, suppose every of you try to draw 10 numbers from the uniform distribution from 0 to 1, every one of you. And because you are randomly drawing the numbers, every one of you will draw a different set of 10 numbers. And every one of you can compute a sample mean. But your sample mean will not be the same as the other sample mean. We have about 30 students here, then we will have 30 different sample means. And then, but there will be some behavior. We know that mathematically, we know some behavior about these sample means. The average of all these sample mean will be more or less the same as the population mean. That's the meaning of the mean of the mean. And besides the mean, we will also have a variance, just as the example I explained before. If every one of you try to draw a sample of size 10 from 0 to 1, every one of you get a different sample mean, and there will be some variability among the numbers. The variance of these numbers that you compute as the sample mean is what I give in this expression, variance of the sample mean. Mathematically, there is a formula for it. What's the formula for a random sample? Any idea? It is related to the population variance.
Isn't it like 1n negative 1 sigma brackets x minus x bar?
That's the formula for calculating a variance, but yeah, but mathematically there is a even more simple formula.
Oh, is it the e brackets x squared brackets negative e brackets x brackets squared?
Yeah, that's the formula for calculating the variance. But for the variance of the sample mean,
Oh, is it like n sigma or just sigma?
yeah, something like that.
Yeah.
It is sigma square divided by
N.
Yeah, thank you. This is the formula for a variance of the sample mean. It is always equal to the population variance divided by the sample size. For a random sample, whenever you have a random sample, if you want to determine the variance of the sample mean, it is always equal to the population variance divided by the sample size. In this example, the sample size is 10, so it will be equal to sigma square over 10. So the variability will be smaller if the sample size is larger. So that means if every one of you, instead of drawing 10 numbers, I ask you to count 1,000 numbers, every one of you. Draw 1,000 numbers, and everyone compute a sample mean. Then more or less, the sample mean you obtained will be very close to each other. Now, in this question, we are asked to compute this expectation of the sample mean, the variance of the sample mean, and what we need will be the population mean and the population variance. And we know the population is uniform from 0 to 1. So, we just do it according to the, starting from the very beginning, from the definition. This is how we compute the population mean. The population mean is the expectation of one particular observation from the population. In general, it is obtained as the integral. This is integral of x multiplied to the probability density function, integrating over the whole real line. This is the formula for calculating a population mean. I guess you should have already learned this before. Right? Now, this is the case when we have continuous type variable, because we are talking about uniform. Uniformly distributed within 0 and 1, so it is continuous. For discrete case, for some other discrete type distribution, for discrete type variable, this will become a sum. But here we have continuous type variable, so we use integration. So to find this for a particular distribution, like uniform 0 to 1, of course, we need to first find out the probability density function. What is the probability density function for a uniform distribution? Anyone remember the form of the density for uniform? Uniform means it is constant, right? There's no preference on any value within the range. It is a constant. What is the constant?
It's x.
Yes?
X.
S is the distribution function. For the uniform distribution, the distribution function is x. But if when we are talking about the probability density function, what is the probability density function? It is constant.
A.
Yeah. From A to B, what will be the constant for the uniform distribution? PDF. If you draw a number from A to B, in general, from A to B, what is the constant for the probability density function? This is related to the length of the interval. Yeah, the reciprocal of B minus A. So this is the general form for the uniform probability density function. It is equal to the reciprocal of the length of the interval. And here, the length of the interval is 0 to 1. Because we have a uniform distribution from 0 to 1. So B is 0 to 1, A equals 0, so it is 0 to 1. But this has a restriction, because it will be equal to 1 only when the value of S is within 0 to 1. Because we have a restriction for the distribution. We are drawing a number uniformly from 0 to 1, so it is always lying within 0 to 1. So this set of possible values must be within 0 to 1. Outside the range, the probability density function is 0 to 0. This is the probability density function for a uniform 0 to 1 distribution. It is very simple. It is a constant equal to 1 when S is within 0 to 1. And otherwise, outside the range is 0 to 0. So that we put into the integral. We integrate S multiplied to the density, integrating over S. Now the integral range here, in general, it is over the whole real line. But now, the integral range will be from where to where? Yeah, 0 to 1. Because outside this range, the density function is 0, 0, so the integral becomes 0 outside the range. So we only need to deal with the integral for S between 0 and 1. And the rest will be elementary calculus. We are integrating x. So it is equal to x squared over 2, evaluated from 0 to 1, and equal to half. So this is how we obtain the population mean for this uniform distribution. Okay? Now, of course, we also need to find the variance. Now, we use the formula we just mentioned before. This is the usual formula we use for finding a population variance. It is equal to the so-called second moment, the expectation of the square of the single random variable minus the square of the expectation This is the general formula for finding a variance. So we need the intermediate step. We already obtained the population mean already as half. So in order to find the variance, we need this quantity, the expectation of the square of a single variable. So again, we use the integral to find an expectation. Whenever you want to find an expectation, if you have a continuous type distribution, it is always computed by using an integral. And if we are calculating the expectation of a square, we just put a square of s and then multiply it to the probability density function, integrating over the whole range of data. So as before, we put fs equal to 1 for the uniform distribution, and the rest will become elementary calculus, so that for the uniform 0 to 1 distribution, the expectation of the square of s is equal to 1/3. Now this is not the end of the story. Remember, this is just an intermediate step to get this done. From my past experience, I find that students, when they are asked to find the variance starting from this formula, after they get this, they just stop. And of course, that is not complete. You also need to use this formula to compute the variance. So we substitute what we have calculated before, the expectation of the square of s minus the square of the expectation of s. So the variance for the uniform 0 to 1 distribution is equal to 1/12. So that finally, we know that the mean of the sample mean is equal to the population mean. The variance of the sample mean is equal to the population variance divided by the sample size, equal to 1 divided by 120. So this is how we get this answer from this question. Is there any question? Just try to understand every step. These are actually quite standard and routine procedures to get all these answers. For a general problem, you may be given another distribution. Actually, you do the same kind of calculation, the same steps, except the density function used will be different, so that you have another integral. But the step, the logic flow will be the same. Any question? Now, let's move on to the question number 5. Now, this question is not difficult, but it is very complex. It takes a lot of time to write down a lot of tedious calculations. But I just try to work out and show you the detailed steps. Now, this time we have a population consists of 5 numbers. So we are given the population. We are already given the population, but it's a very small population containing 5 numbers: 3, 7, 9, 11, and 15. And this distribution is symmetric about the center, 9. The population mean and median are identical, equal to 9. So in part 1, we are asked to calculate the population mean. So since we already have the population values, 3, 7, 9, 11, and 15, So the population mean will be just the average of these 5 numbers. When you have the complete list of numbers in the population mean, of course, is just the average of these numbers. So in part 2 is the clumsy part. We are asked to write down all possible samples of size 3, which can be drawn randomly without replacement. Yes?
Yeah, for part I, the first one, and not just say it's 9, because the median is 9. So without any calculation.
We calculated the population mean, so this is the population mean.
So not just say it's 9, because it says mean and median are identical.
Yeah. So the median is also equal to 9 because it's symmetric distribution. For symmetric distribution, the median and the mean will be the same.
So we not just do any calculation, just say it's 9 because the median is 9.
Well, we are asked to calculate, so I just simply do the calculation. But you can argue that it is already given in the question.
Yeah.
Okay. Any other question? So in part 2, we need to list out all the possible samples. So how many possible samples are there if we draw without replacement for the 5 numbers? Now, first of all, you need to understand what it means by the sampling without replacement. Without replacement means you draw a number, you are going to draw 3 numbers. Just imagine that you draw it sequentially. You randomly draw 1 number from this 5. And after you draw the number, we don't put it back. That's the meaning of without replacement. After you draw a number, we don't put it back. So suppose the first number you draw is 7. Then what remain in the population will be only 3, 9, 11, and 15. And then we will draw from this remaining 4 for the second number. And then we draw from the remaining 3 numbers. Then we get a sample. That's the procedure of the so-called sampling without replacement. In contrast, there exists another way to draw sample, which is called sampling with replacement. Sampling with replacement means after you draw a number, we'll put it back. And I draw the number again. So every time you are drawing from the same 5 numbers. So it is possible for us to obtain repeated numbers if we are drawing with replacement. But now we are drawing without replacement so that there will be no repeated numbers here in the sample. So we can just list them one by one. We start with the 3 smallest number. This is one of the possible samples we can draw without replacement. 3, 7, and 9. The next possible sample may be we change 9 into 11. We draw this sample. Or 3, 7, 15. 3, 9, 11. 3, 9, 15. 3, 11, 15. We keep on listing all the possible sample of size 3 from these 5 numbers. 7, 9, 11. 7, 9, 15. Every time I put this kind of list, I always miss something. 3, 7, 9, 7, 9, 11, 7, 9, 15. 7, 11, 15, yeah. 11, 15. And finally, 9, 11, 15. So this completes the list of all the possible sample of size 3 if we are drawing without replacement from this sample of size 5. This is just a brute force listing. But we can just check the number of possible samples we can get. The number of possible samples is 5C3. equal to 10. I guess all of you, have you ever learned about this? Yeah. We have 5 distinct numbers. We draw 3 out of them. The number of possible combination is 10. It's 5C3. So we have 10 possible samples. And the question, we are not just asked to list all these samples. We are asked to compute the sample mean of each of these samples. Just imagine that you are asked to draw 3 numbers out of these 5. So you have a bag with some papers written these numbers put into the bag, and you are asked to draw 3 papers out of this bag. You get a sample of size 3. Then based on your sample, you can compute a sample mean of your sample. Imagine that if you got this number 3, 7, and 9, then the sample mean will be the sum of these 3 numbers divided by 3. And if the sample you obtain is 3, 7, and 11, then the sample mean would be 21 divided by 3. Similarly, if the sample you draw is 3, 7, and 15, then the sample mean will be 25 divided by 3, and so on. So this is the list of the samples that we can possibly determine, and the sample mean of each possible sample. Now, because we are talking about random sampling, we draw the sample randomly. So we have certain chance to obtain each of these sample or each of these sample mean. So how likely that we will obtain this sample so that we get this sample mean? What's the chance that you will get this sample? Yeah, 1/10. Each of them will have the same probability, 1/10, to be drawn. So that means for this small scale scenario, if you are asked to draw a sample of size 3 from a sample of size 5, from a population of size 5, and then compute your sample mean, you have 1/10 chance to get this sample mean. You have 1/10 chance to get this sample mean. You will also have this 1/10 chance to get this sample mean. So this is what I mean the behavior of the sample mean. The behavior of the sample mean that you may obtain. And we can study the behavior of it by finding its expectation and variance. Instead of using the formula, we can directly list out all the possible samples, all the possible sample means, together with their probability to find the expectation of them. Just imagine that every of you is asked to draw a sample of size 3 from this population. And then every one of you get a sample mean and you report the sample mean to me. I take the average of all your sample means. That is the expectation. So how can we get the expectation of the sample mean based on these numbers? We multiply each possible value to the corresponding probability, and then do it for all the possible values and add them up. We multiply every numbers to 1/10, each of these numbers to 1/10, this number to 1/10, and we have 10 terms of this product. We add them up. What will be the value? Without doing the calculation, just make a guess. What will be this expectation?
None.
Yeah, very good. it will be equal to 9. You can try to do the calculation, the Kamsi and TDS calculation. You will find that the sum, the expectation of the sample mean here computed is equal to 9. Because we have the mathematical fact, expectation of the sample mean is equal to the population mean. And we already got the population mean being 9. And we can also compute the variance based on these numbers. Right? So we compute the variance. And to compute the variance, as I mentioned before, the first step and intermediate step is to find the expectation of the square of the value. So we multiply. This time, we take the square of each possible value, multiply to the corresponding probability. This time, for every numbers here, we take the square and then multiply to the probability. And add them up. For these 10 terms, we will obtain the expectation of the square. And it is equal to something like, I can't remember, so I need to refer to the solution. $7,530 divided by 90. You can try to work out the calculation to verify that the expectation of the square of the sample mean is equal to this. So that the variance of the sample mean will be equal to expectation of the square of the sample mean minus the square of the expectation of the sample mean. This is the formula for finding the variance. And finally, we obtain the variance of the sample mean. Okay? So this is how we answer this question. List out all the possible samples, compute the sample mean of each sample with the corresponding probabilities. We can find out the expectation of the sample mean and the variance of sample mean without referring to any mathematical formula that I've shown you before. In fact, this variance actually is not equal to this. In the previous question, I've already mentioned about a nice formula that the variance of sample mean is equal to population variance divided by the sample size. But it don't apply. It didn't apply for this example. You can check to find the population variance and then calculate this. You will find that it is not equal to 2.667. Do you know the reason? Because we are joined without replacement here.
So it's n minus 1 you're dividing by.
Yes?
Would it be sigma squared over n minus 1?
Not exactly. There will be a correction factor. Actually, it will be equal to n minus small n divided by n minus 1 sigma squared over n. We call it the finite population correction. Now, notice that this formula, sigma squared over n, as the variance of the sample mean, it applies for the case when we are joined with replacement. If you are joined with replacement, every time you are joined from the same population without putting things back, every time you put things back and then join from the same population, then the variance of the sample mean will be equal to this. That's the mathematical fact for that case. But in this example, we are joined without replacement. Joined without replacement will be slightly different, especially when the population size is not large. Then in that case, the mathematical fact will be changed a little bit. The formula for the variance of the sample mean will become this, with a so-called finite population correction factor, where this capital N is the population size, small n is the sample size. You can try to verify this by finding the variance of the population, substitute into this, you will find this number. But I guess all of this will be taught in more details in the lecture. Okay. Any question? Okay, just let me know whenever you have any question or you encounter any problem in understanding the course material. Just feel free to jump me an email. Okay? Okay. So see you next week. Thank you. Bye-bye.
Thank you.
说你借了5个骰子，然后随便喊几个几，然后你是骗人就开始，然后所有的合准的人都会玩那个，然后后来有个小姐姐就甩骰子特别牛逼，她打不是我的那个丈夫打的，丈夫，然后他们就那个，然后到底那是谁的？我说昨天上课，我说他要跟啊，对。
拜拜。